Today we follow up Newton's first law with, logically enough, Newton's second law. From the inquiry lab, we were able to see that the acceleration of an object is 1 over the mass times the force. Put differently, if you double the force on some object while keeping the mass constant, then the acceleration will double as well. So if you double the force, you double the acceleration as long as the mass is constant. If you double the mass on an object, the acceleration is halved, as long as you keep the applied force constant. And we see the acceleration points in the same direction as the applied force, which is not silly, but we should say it. What the experiment couldn't show, but it turns out to be true, is that the relevant force is the net force. That is, the vector sum of all applied forces. So, graphs are shown of the velocity versus time for two identical train engines on a straight track. Positive velocity indicates the engine was traveling east. The scales on both axes are the same for the graphs. On each graph, a point is marked with a dot. A student comparing the net force acting on the engine at the identified points on graphs A and B states, I think that B has a larger net force since the net force on A at the identified point is 0. What, if anything, is wrong with the statement? If something is wrong, correct it. If the statement is correct, explain how you know. Take a couple of seconds to think about this, and then we'll go over it. Okay, the student is incorrect. The net force depends on the acceleration, not the velocity. And we can see that the acceleration on a VT graph is the slope. It's pretty easy to see even by eye these two lines are parallel, so their accelerations are the same. So the net force is the same. So what about the 0 here? Well, the 0 here tells us that the velocity is 0, because that's when the velocity is crossing the t-axis. But the net force is not dependent directly on the velocity, but on how the velocity is changing, and it's changing in the same manner at that moment. The figure shown below showed two identical curling stones, the playing pieces in the sport of curling, that are being pushed horizontally by the thrower. The instantaneous speed and acceleration of the two stones are given. Positive direction is to the right, and ignore the friction between the stone and the ice. So we have v is 3 meters per second, but a is 1 meter per second square. Here is v is 2 meters per second, and a is 2 meters per second squared. Is the magnitude of the force that the thrower is exerting on the stone in case A greater than, or less than, or equal to the magnitude of the force the thrower is exerting on case B? So take a look, and we'll talk about it in a couple of seconds. Again, we're going to use that the net force depends only on the acceleration at the moment. Since B has a greater acceleration, we know that B is a greater force, and therefore the force on A is less than the force in B. The second law is much more traditionally commonly written as F net equals ma. This is the one that everybody remembers. If you go home and ask your parents if they took physics, and if they did, if they remember any equations from it at all, they'll probably tell you F equals ma is the one they remember. Everyone for hundreds of years have memorized it this way, and so it's worth talking about. But I would agree with your textbook, a rare enough occasion, that the other form is actually more useful, all right, intellectually. The combined effect of a set of forces is to produce an acceleration. In other words, we find the net force, and that tells us where the acceleration points, instead of here, which kind of implies that we have the acceleration and then derive something about the net forces. It doesn't really matter, but the forces are the causal factor, so I think that the other form is intellectually more consistent, but they're functionally equivalent, and this is the one that everybody remembers. All right, a cart is pulled to the right with a constant steady force. How will its acceleration graph look? And we have the 4 of them down there, 3 of them down there. All right, well, since the force is steady, it's constant, and the acceleration depends on the force and the mass, which is not changing, so the acceleration should be constant, so we should get this one. Indicate with a blue arrow the direction of the acceleration that results from these forces. So we assume these are the only two forces acting, and we remember that the acceleration is F net over m, so I have to do a vector addition. So if I take this one and then I put the other one tip to tail, which looks to be maybe that long, then the net force that comes out is this, and we know that the acceleration will point in that same. We don't know how long it's going to be because we don't have an acceleration scale, but it has to point in this direction. This, of course, is a classic tug of war where the people pulling to the left pulled harder than the people to the right, so they moved the knot towards them. Same directions. Indicate with a blue arrow the direction of the acceleration that results in these two forces. Again, what we want to do is get the net force, which points, let's see, well, we add the two like this. So the net force is the tip-to-tail addition, and we know that the acceleration points in the same direction. Since we don't have a scale, we technically could just use the purple arrow as the acceleration, since we don't really know. But I like better to contrast here that it's in the same direction, might be a different magnitude, or actually has to be a different scale since it's measured in different units. Third time, same rules, so again, do the same sort of thing. Here we might say that we add the, let's take this as our first one and then add this and then add that. So we get something like that and then something like that. So our net force points in that direction, and therefore the acceleration also points in that direction. A 40-car train travels along a straight track at 40 miles an hour. A skier speeds up as she skis downhill. On which one is the net force greater? In this case, the net force must be greater on the skier, which is a little counterintuitive because, after all, the 40-car train is so much more massive. It's in the tens of thousands of kilograms, and the skier might be in like 50 kilograms. And so it should be a lot harder to move the train than it is to move the skier. And that's true. Getting the train started was harder than getting the skier started. But at this moment, the train is moving at a constant 40 miles an hour, and therefore the acceleration is 0. So the skier is speeding up, so the acceleration is non-zero, so the force on her is more. Of course, the problem here was not explicit. Is it really constant? It only says at some moment. So if you thought, well, I don't know, then the answer would be you can't tell. So you could easily defend this if you don't believe the train, if you don't know that the train is constant, which is technically not in the problem. All right, the SI unit of force, the metric unit for force, is called the Newton, maybe sort of not surprisingly, symbolized by a capital N. Little weird, and the way it works, written with a lowercase n in the word Newton, but symbolized with a capital N. The International Standards Organization is afraid that if you put a capital N here, you might think we're talking about the actual person, Isaac Newton, coming back from the dead like some sort of zombie physicist. So we don't do that. We use lowercase to say it's some inanimate thing, and uppercase N because, well, mostly because we don't confuse it with nano. All right, we define it so that the force of 1 Newton will impart an acceleration of 1 meter per second squared to an object of 1 kilogram mass. That is, that 1 Newton is 1 kilogram meter per second squared, and we'll use this a lot. As an aside, the British unit of force is the pound, which you're familiar with. You might think of the pound as a measure of mass, but it's not. It's a measure of weight, so therefore it's a force. The British unit of mass is called the slug, or sometimes the stone, depending on who you want to talk to. And is a little weird, and we're not going to get into. So if a net force of 24 newtons is applied to an object and it accelerates at 1.7 meters per second square, what is its mass in kilograms? Well, we're going to go through the idea that F net is ma, and therefore 24 newtons is the mass times 1.7 meters per second square. So 24 kilogram meter per second squared over 1.7 meters per second squared is m, which turns out to be 14.1 kilograms.